Doing well.
Cool. Hopefully the network stays up. There was like a big car crash the other day late in the afternoon near my house, and it took out power and cable and everything. It took them a long time to patch it back together, and then yesterday it worked. It was working, and then just as we were getting my 172 class started, it went out, like completely gone. And it was like, what the heck? So call the service provider, and they're like, "Oh, we're coordinating our work in the evenings because people are working from home and they need work during the day. So we have it patched together during the day, and it's not working in the evenings." It's like, oh, great. So hopefully we don't have issues tonight. Remember, I was asking you folks if you had heard anything about any changes to the format for next semester, if we were gonna, if anything has been issued to you as far as classes being online or in person or anything like that. I actually received this kind of odd questionnaire from the university asking what the plans were for classes in fall. So I think there might be something lingering in the next weeks or month or so with what they're doing. I got the impression from what they'd sent out that they might be leaving it up to each instructor to decide if the course is going to be hosted in person or remote or some sort of hybrid version or not. So I asked for clarification on it. So kind of curious how it's going to sort out. So I have a kind of a cool problem to go over with you tonight that is probably the best way to describe it is a Sprott problem, because it's kind of as it's as pragmatic as you can get or realistic as you can get, but it's still conceptual, still theoretical. But hopefully it'll start adding a little bit more clarity to this idea of elasticity and what a strong form is and what a weak form is, where they're essentially a weak form is a subset of the strong form, where it's a small subset of a domain within a larger domain, where the equations are essentially, they still hold true, but they look a little bit different. So we create some relationships saying that things are equal to each other, and we just have to trust that that's really true for it to work out. So let's go over to our our board. Man, April 8th already? Is anyone graduating this semester? No? Bummer.
I'm supposed to be graduating, which I am.
the supposed to got me a little worried there.
I don't know. I guess it's like a long time coming, so I put it that way.
Okay. So your thesis is already submitted, or undergrad?
It's supposed to be for undergrad.
Okay. Well, congratulations. Okay. So what this problem is going to do is it's going to look at one-dimensional elasticity. And I'm going to call this strong form. And we're going to kind of lay out this problem of what it looks like. And then we're going to look at the variational principle for 1D elasticity. So if you remember, the variational principle is the potential energy functional. So we'll look at that. And that is essentially a different, it's considered a weak form of what we're going to show here, because it's a subdomain where we're using weighting functions and things like that. And we're essentially going to work through like a proof showing that the variational form and the strong form basically whittle down to the same thing. So it shows that they're equivalent for when we do future endeavors, when the variational form might be easier for us to solve. So instead of talking about potato, we're going to talk about something a little bit more pragmatic, and we're just going to talk about a this arbitrary beam. We're going to say this beam has a length of L. And we're going to say that it has some sigma naught stress on it. We're going to say that it has a body force as a function of X. So X in our positive direction. And down the center line of this, so there's a center line of it. And we're just going to say that there's this E of X comma A of X. And let's write what some of this stuff is. So let's write first what the problem statement is. So let displacement along the X be a displacement field. Strain along the X is going to be a strain field. And sigma X is obviously a stress field. As a function of X as you go down this. Where E of X is Young's modulus. So if I'm saying E of X is Young's modulus, what type of material am I implying here?
Isotropic.
Yeah. So A of X is just simply area. B of X is a body force. And L is obviously the length. So when we say A of X, for instance, you know, that's at a particular point. So if this is circular, you know, it would represent the area of a particular point along this x-axis. So it's a function of the length, and that goes for the body force or Young's modulus too for this particular case. So this Young's modulus is not necessarily constant, because if we could feed this a vector, so it could change down the length, but it's just anything. And then also we need to state our domain is simply omega is equal to 0 to L. So obviously, here is our 0 point, and then all the way out at the end of our beam is L.
So even though we have a 3D object, it's called one-dimensional because our domain is just purely in the X. It's only going to be deforming in the X. That's why.
Yeah, the problem we're looking at right now is we're only looking at deformation in the X direction for this particular problem. So our boundary conditions are BCs. We're going to state our displacement at 0 is equal to 0, and that's shown with the with this fixed boundary. And we're going to state that the elastic modulus at L times the first derivative of our displacement at L is equal to our stress. Our kinematics is strain as a function of x is equal to derivative of our displacement with x, which is equal to this u prime of x. So I think I've mentioned this to you before, right? That strain is simply the derivative of displacement. Have I mentioned that to you? I may have mentioned it, but not written it. Hooke's law, or we can call it our constitutive equation, is simply stress as a function of x is equal to our Young's modulus as a function of x times our strain as a function of x. So there's nothing new here, right? This is sigma EE. I'm just saying that it changes. And based on these kinematics that I've just spelled out and these boundary conditions, this is also equal to E of x u prime of x. You guys aren't jumping up and down with excitement. I was super cool when I learned this kinematics thing. We never talked about this in undergrad. Did you guys talk about this in undergrad? That if you have a displacement field, you just take the derivative of it and you have strain?
I feel like Holman might have mentioned it in passing, but
Okay.
definitely never like went into it.
So
I
yeah.
remember some of it.
Do you? Okay.
Yeah.
Very cool. So that must be newer, because when I went through undergrad, they didn't mention this. So I think of it now kind of like from like a physics perspective, right? When you have a displacement, you can go to a velocity and acceleration. You can kind of go back and forth using calculus. Well, displacements and strains are the same way. It's really cool. So now I want you to consider a subdomain. Blue. Now consider a subdomain. And we still have our body force. Now we're going to say the subdomain of x is equal to A and x is equal to B. And in this subdomain, we're going to say that omega prime is contained in omega. And omega prime is equal to A to B. Force equilibrium in our subdomain omega prime implies that the integral from A to B of our body force along x plus our stress at B times our area at B minus our stress at A times our area of A has to equal 0 in omega prime. This is just equilibrium. So just kind of reorder this a little bit. Sigma B, AB minus sigma A, AA plus the integral of A to B, body force along x dx is equal to 0. Now we take the integral of this side, and it is simply the sigma, the integral of A to B, sigma x, ax prime dx plus the integral of A to B, bx dx is equal to 0. Or you can write it as the integral of A to B of sigma A prime plus B dx is equal to 0 for all omega prime contained in omega. Now we assume that sigma A prime plus B is equal to 0 in omega. Sorry, in omega prime. And further assume that sigma A prime plus b is equal to 0 in omega. For the governing equations. So we're going to say this is 1a, and this is sigma x, ax prime plus b of x is equal to 0, or e of x, a of x, u prime of x prime plus b of x is equal to 0 for all x from 0 to L. 1b is strain along x is equal to u prime of x. We've already said that. And 1c, we're going to say that our stress along the x is equal to our Young's modulus times our strain. Now look at boundary conditions. We'll call this 1D. U of 0 is equal to 0. And this is a essential boundary condition. And the stress at L is equal to sigma naught, or the Young's modulus at L times the derivative of our displacement at L is equal to sigma naught. This is a natural BC. Okay. So all we did was wrote out the basic equations and how they relate to each other for this 1D elasticity as a function of strain in Hooke's law. And looking at our forced equilibrium where we have a body force and then we have an external force that's causing a stress. So this could be written differently, right? So we have sigma naught. This very well could be, stress is equal to force over area, right? So this could be written as a force here rather than a stress. Our equation would look a little bit different, but it's essentially what it is. Now, does this equation right here look familiar from quite a few weeks ago when we were looking at line integrals a little bit? These are functions of x, but back then I told you that this body force was a volume, right? And this was an area, which still holds true. We're not looking at that right now. We're just assuming that this body force is acting linearly along the x-axis. But this is essentially what turns into what the finite element solution is trying to solve on a incremental perspective and small little sub-slices in the domain. Or in some of the codes and things that you look at, it'll look like this in EA, U prime. This term right here ends up being a fourth order type polynomial that you try a differential equation when it's all written out. So this first term here, and that's where the complexity really comes from, is this first stiffness matrix, if you will, because remember this E of X could be a 9x9 C matrix, right? We've simplified it and we're just saying it's an elastic modulus, and yeah, it may change as a function of X, but that could be an 8x8 or a 9x9 stiffness matrix hitting our area, so that it gets very, very complex. But you see here, we already have the derivative of our displacement, and then we have to take the derivative of that whole thing. So we end up getting some pretty high order boundary value problems that we're having to solve for. Okay, so we know what those equations look like. We know, essentially. Write it out explicitly here. Problem with not having a giant board. Okay. So let me write this out again here a little bit differently. Well, it's the same thing. I'm just going to reorder it because it'll look the same when we're done. Sigma naught is equal to EL U prime of L. So when we're done with our proof, we're going to end up with this. So we're showing that the 1D elasticity strong form 1D equation ends up turning out the same when we look at the variation of. Okay. So keep that in mind. Now we're going to look at the variational. Variational principle for 1D elasticity. And remember, the variation of displacement is equal to the potential energy functional. And did we talk about what a functional is?
Something was written out as a functional, but I don't understand what word means.
It's a family of functions is the best way to think about it. It's not a single function, it's functions plural, and there's a family of them associated with it, depending on where you look at it. And I think the best way to kind of, the way I've rationalized it was the path independence topic, where you're going from A to B, and the path wasn't necessarily important. It was just that you got to the same point. You just had to ignore, how you got there. But you could use the different functional. Hopefully I'm not losing anybody. Path independent, say we have point A, we have point B, and if something was path independent, it meant that it doesn't matter how you get from A to B, if it was a straight line on the black path, or if it was a crooked mile from A to B, or if it was something from, B to A. The path doesn't matter. So one of the ways you can think about it is every one of these paths is a function. So this whole system would be considered a functional. It's a family of functions that give you the same results from A to B.
And can you define any group of functions as functionals?
They have to have the same basically boundary conditions. and they have to be the same result going from one point to the other point or that point back. But what it's stating is that we can say that these three lines right here are equal in that they all get us from A to B. We can't state that any point along them is equal. We can state at A and B, they are equal. And it doesn't matter which direction you go, they will be equal. But at any point along the line, down the path for them, they're completely invalid. You cannot associate the functions that way. You can only.
So it's kind of like putting in like a place on a GPS and then picking a different path to go on depending on the traffic, where any path that gets you from where you are to where you're going would be like a function within the functional.
Kind of. You can only compare the start and end point.
Okay.
You can say that they get you the same result at the starting point, at the starting point and at the ending point, or if you're talking about integrals over the same domain. But if you change the domain, all bets are off. Right?
It's kind of like if you lift something 5 feet off the ground. It doesn't matter if you kind of took a squiggly line to get it 5 feet off the ground. Potential energy from where it is to the ground is the same.
Yeah. Yeah. So, I mean, from the perspective of this, we're creating a boundary condition between A and B, right? So this variational principle is we're gonna change what these equations look like, and they're still valid from A to B, but we can't create a subdomain and say A prime, B prime, and say that A to B is the same as A prime to B prime. That's not the same. It has to be the same in conditions. So, family of functions within a function. And we basically minimize it, right? That's the whole idea of this. And so this is equal to, let's not use red. Red's supposed to be bad, right? So the work internal of U minus the work external of U. And there's a whole lot of stuff involved in here that we're not going to get into. If we were talking about advanced dynamics, then we'd be talking about how virtual work plays into this. So there's a lot. This is kind of a loaded statement here. So just kind of take it with a grain of salt. This internal work, this guy here is stored or strain energy. So typically, if our material has an elastic modulus, like a steel, and it has some linear slope to it, it's going to store energy, right? Because when you release the load or you remove the stress based on the load, it's going to recover that potential. That internal potential energy is going to come back. So the work internal as a function of displacement is equal to the integral of V U naught dV. And this dV is a dx. So we could write this as the integral of the volume u naught a dx, but it's typically written as a volume term. But you could expand it. So this is an a, not a delta, area dx. Where u naught is the strain energy density.
So is A the area of the like beam section that we're,
Yeah. Yep.
Okay.
Same A. And assume that the A is not constant. It varies. It's not a constant cross section. So to add a little more context, we'll kind of say that we're dealing with a complete linear region. Sigma, strain. The slope of this line is our elastic modulus. And then you notice I'm not drawing that, right? Because it's not valid for this. We're only talking about this 1D elasticity functions that we're describing right now are valid for the linear regions of the material. Right now. So, and everything that we're talking about is still valid if we go nonlinear. It's just you take everything that we're doing here and say plus the plastic stuff that goes on. So it's the linear plus the plastic, just like when we were talking about total strain, like in MU180, it was always the linear plus the, or the elastic plus the plastic. The strength assessment stuff works the same way. It's your elastic plus your plastic flow, which is the J2 flow theory. So we're focusing on solely on the linear portion. So the area under the curve is equal to 1/2 sigma our strain. Our strain energy density is equal to the integral from 0 to our strain of sigma d epsilon, which is equal to 0 to our epsilon value of e epsilon d epsilon. So our W, our work internal, work int, U is equal to the integral of 0 to L, U naught, A dx, which is equal to 0, our integral from 0 to L, 1/2 sigma epsilon A dx. Where did my mouse go? There it is. This can be further simplified to 0 to L, 1/2 E area epsilon squared dx is equal to the integral 0 to L, 1/2 E is a function of x, A is a function of x, U prime squared dx. remember that string is equal to our u prime. Right, that's where this is coming from. And now we're going to look at our work external. This function of u is equal to 0 to L. And guess what terms this is going to be for external work? What do you think it is? It's our body force. U of x dx. So this total thing here work done due to B of x, a body force, plus sigma naught AL UL dx this is work done due to tractions at x equal L. I think we wrote this out before, but I think it's worthwhile to write it again in context here. So the theorem slash principle of minimum potential energy TMPE theorem minimum potential energy is among all kinematically admissible displacement fields. And I'm going to use squiggly of x. I'm going to write it this way with that bar, meaning this could be a matrix, but this is a common way of writing that it could be a vector field. So among all kinematically admissible displacement fields U of x, the one that minimizes phi of u is the solution of the boundary value problem. So kinematically admissible displacement, KAD, requires that your displacement field must satisfy essential boundary conditions. So this is equal to the integral from 0 to L, 1/2 E of x, A of x, this is actually U squiggly prime squared D of x minus the integral of 0 to L B of x U of x D of x plus sigma naught A L U L. So what we're writing out here is this U squiggly means we're not talking about any specific displacement, because we have to find the one displacement field that minimizes this functional. Where
So this is a step that finite element code, like all finite element code are basically all go through to.
no, they're not doing this.
Okay, so finite element code would use a different approach than this.
Yeah, the finite element code is using the Rayleigh-Ritz-Guillory method, which this is for Monday. That's the next step after this. This is another way that you can solve the elasticity boundary value problem. So we have an elasticity boundary value problem. We can solve it by Taylor series. We can solve it by the theorem of minimum potential energy, or another way we can solve it is by the Rayleigh-Ritz-Guillory method, and that's the most common way that they're going to do that. But all of these, the Taylor series, the minimum potential energy theorem, or the Rayleigh-Ritz, they can all this mathematics can be applied to an element, a very discrete small element.
That's what I was wondering, because the weak form seemed to discretize it. So I was wondering if some finite element code used.
Well, if you think about this, is you could break this integral from 0 to L up into fractions of 0 to L, right? We could have 0 to 1/10 L, 0 to plus 0 to 1/9 L, or something like that. You could break it up into multiple slices and sum it together, and you could look at a particular slice. You could get a solution for each one of those slices, right?
Yeah.
Do you kind of see that? And that's what we did with up here, where we said, let's look at this subdomain right here.
Yeah, that's what I was talking about. When you broke it up to a subdomain for the weak form.
Exactly.
You're discretizing it. Yeah.
Yeah, that's exactly what you're doing. You're discretizing it. So we could do that thousands of times and look at that, and it's just a summation of it. So we're taking results of each one of them. So you could, you could, solve that problem that way. It's just a solution to a boundary value problem, and that's kind of the crux of this whole topic of this class. That the finite element method is just one particular way of solving this problem, but the problem is the same. It's an elasticity problem that we're trying to solving. It's it's a stiffness matrix, our times a strain, which we now know that our strain is the first derivative of our displacement field. And oh yeah, we have to take into account these body forces from Mars, like magnetic fields and things like that, if we want to be super accurate, or we can just blow it off and ignore it. But we can't, the mathematicians would be, very angry at us if we just, said that, oh, we can use these same equations under these in these subdomains without using different terms and things like that. Now,
yeah,
some complexities are going to come into this when we look at the Rayleigh-Ritz-Gullurkian method, and that's where that craziness of the mapping to go from one coordinate system to another coordinate system and creating our element stiffness properties and how those elements relate back to this. That's a whole thing all in itself.
okay, yeah, I think that makes sense. That's helpful.
But it's, yeah, okay. Okay. So we're saying that this holds true where this term is this. I think it's a delta. It's hard to read my own writing sometimes. I feel sorry for you guys. A delta is equal to this displacement. We're saying this displacement is 0 is equal to 0, where our displacement is C0 continuous from 0 to L. So if we remember, this C0 meant that essentially our first derivative of our displacement is continuous through that entire domain. We're saying our domain is 0 to L. And if we have a displacement field that exists in there, and if we take the derivative of our displacement field anywhere from 0 to L, it's going to exist. We don't have any holes. We don't have any Kronecker deltas shooting up to infinity. None of that is in this domain. That's what this is saying here. So we're good to go. So with these two true, then minimize this. For our displacement field to get the boundary value problem solution. Okay. So let's go through that. It's kind of long. Okay, we'll do it. So consider that this is equal to 0 to L 1/2 E A U prime squared dx minus integral from 0 to L B U dx plus sigma naught A L U L with our displacement contained in our delta. So in this guy here. So contained in our delta. So U lives in there. So now we're going to say our delta U is equal to 0 for a stationary, well, we're going to call this a minimum point, so that our delta equal to 0, therefore 0 to L, 1/2 EA 2 times U prime delta U prime dx minus integral from 0 to L B delta U dx plus sigma naught AL delta U of L is equal to 0. And this is for all delta U contained in our volume. And this delta U prime, this is commonly known as a virtual strain field. Right, because U prime, the derivative of our displacement, U prime, we've saying is strain. And now we have this delta U prime. And the only thing delta really is it's essentially this made up kind of subdomain, right? Can you guys see that? We're saying that this delta is equal to our displacement, and we're saying our displacement field is equal to 0, 0, okay, it's a boundary condition. And that our displacement field is continuous from 0 to L. Okay, so it's just somewhere in there. Our delta is somewhere in there. And so this delta U prime is just considered this virtual strain field somewhere between our 0 to L. And we're going to say that our volume is equal to delta U, or we're creating the domain for it, better if you will. So our delta U is, we're stating our problem. Delta U is continuous in C0 from 0 to L, and our delta U of 0 is equal to 0. So essentially, this is the same thing that we wrote here, right? We said delta was here, and now we're saying, now we're calling this V, where we're saying this delta U lives in the same space. I mean, it's C0 continuous from 0 to L, and we're creating a boundary condition saying, okay, this delta U at 0 is equal to 0. So it's essentially the same point, but we're going to call this V now. And therefore, integral from 0 to L, EA U prime delta U prime dx is equal to 0 to L B delta U dx plus sigma naught AL delta U of L for all delta U contained in V. And this is called the variational weak form. it's the exact same equation, except we've thrown this delta U in there, right? Where our displacement U belongs to our delta space. When I say space, I mean like a mathematical space. And delta U prime belongs to our V space. We're basically just saying we have this beam, we're breaking it up into subdomains, if you will, and we're using some different variables to say that we're looking at a different space, or we're looking at a different slice of it. Is all we're doing here. So now now integration by parts. So we have integral from 0 to L EA U prime delta U dx is equal to 0 to L B delta U dx plus sigma naught AL sigma UL. So we get EA U prime delta U 0 to L minus the integral from 0 to L EA U prime delta U dx is equal to, I'm just going to go like this. So this whole guy here, so we can save time. And EL AL U prime of L delta U of L minus E of 0 A of 0 U prime of 0 delta U of 0, which was 0. We defined that. It's equal to, and we'll just say equal to plus, so you know that's all that. And then we have integral from 0 to L EA U prime plus B integral of U delta U dx plus sigma 0 A L delta U of L minus E of L A of L U prime of L delta U of L is equal to 0. And I'm going to put a star next to, or a double star next to this guy. And now we say, pick a delta U bar such that delta U bar at L is equal to 0. Then integral from 0 to L EA U bar prime we don't need this there. Prime plus b dx is equal to 0. This gives us e a u bar prime plus b is equal to 0. Which gives us e a u prime plus b is equal to 0 in our domain of 0 to L, sub into our little equation. Then we can state that sigma 0 AL minus EL AL U prime of L delta U of L is equal to 0. And we get sigma 0 is equal to E L U prime of L. And that was the same thing that we have above. So therefore, strong form is equal to variational form. And this right here is the traditional boundary condition. So with all of this stuff, we've been making, it's all pretty straightforward, right? It's Hooke's law. It's stress, strain, displacements. But what one thing is really the key to solving all this, making sense with it? What do you need for actually getting a real answer? Like if you wanted to get a numerical answer.
The boundary conditions.
Boundary conditions, which typically when you're doing this stuff, you set those, right? You have your you're creating your tractions. So you're holding the part somehow, or you're holding the component and you're applying a load of some sort. So you're applying those tractions. So those are usually known. Those boundary conditions are known. But what we don't know is, and we have these relationships, right? So ultimately, if you're trying to design a part, you may be designing it based on stress levels. You want to keep your stress below a certain value, right? It's like, okay, so stress is equal to my elastic modulus times my strain. Okay. So So I can calculate stress. I know my elastic modulus is, that's my stiffness matrix. I don't know what the strain is. I need to find my strain. And we now know, or we're reminded by, strain is the derivative of my displacement field. So it's the displacement field that we're after, right? If we have the displacement field, we have the keys to the kingdom. We have whatever we want. That's the solution we're looking for, is the displacement. But I haven't laid any of this out saying displacement is equal to this. I'm giving all of these other relationships that are, I don't want to say they're meaningless because we need them, but we're not getting the answer, right? We're nowhere closer to the answer at this point, because we need the stupid displacement field to get an answer. That's what we care about. How are we going to get this displacement field?
Solving the differential equation.
Yeah, we've got to solve the DE. And when we start looking at the Galerkian method, we're basically going to make some assumptions and guesses at it. So they're going to be informed, basically kind of like this whole weak form thing for this variational principle, where we just created this. To me, this seems very almost arbitrary, right? This variational form here, because we said, okay, we have these strong form solutions, and now we're just going to say, oh, okay, let's not call this a displacement anymore. Let's call it this this delta space, right? And in this delta space, I'm going to add this other variable, and then I have this delta, and then we're going to say everything's equivalent in the end. So we're essentially making a guess so we can simplify this solution. And that's essentially what we're going to do is we're going to make some educated guesses that the mathematicians have figured out for us, that told us work, at what those displacement fields are. And then we're going to check them through our system equations to see if the checks and balances work out. Does our constitutive law hold up? Do we have a continuous strain field? Is the first derivative of our displacement field continuous in the domain? So you're going to do all of these checks to make sure that it works. Because if we were to plug numbers into this, that's where it all could fall apart, right? Like if, we said that this whole thing was equivalent. Let's go all the way back to our beginning. We said this is all well and fine at x equals a and x equals b. We've said that between a and b, if we get values in there, they're valid for, we can say that they live in the domain between 0 and L. Maybe I should have wrote that here, x equals 0 and x equals L. So we've picked a subdomain here, and we've said, yeah, this subdomain is valid between 0 and L, but we haven't made a claim that a subdomain is valid yet. We would have to go through this whole routine to show that that is true. And as you know, it's almost like funny math, right? It's going to be, because it's but we'd have to do those checks. We'd have to do those checks and balances to say, yes, this displacement field can exist in this subdomain, and our constitutive relationship is still valid in this subdomain, and our stress strain laws are still valid in this subdomain. So you make a guess at it, and you do those checks, and if it works out, then that is a solution. And remember, from differentials, you could have a non-unique solution, right? Which isn't what we want, but that is plausible. So okay, so that's it for tonight. I think on Monday we're gonna we're going to introduce, it's called Rayleigh-Ritz-Galerkian method. Let me write it out. So those of you.
So it's like 3 people?
It's multiple things together, but this, let me write it down. Let me get to the bottom here. Rayleigh-Ritz, and it's commonly known as the Galerkian. That's this, there's multiple variations of it. So it's called the Rayleigh, R-A-Y-L-E-I-G-H, Rayleigh-Ritz. And we're going to be looking at the Galerkian, G-A-L-E-R. I think it's E-R-K, Galerkian method. And this is a numerical. Or approximate solution to a boundary value problem. This Rayleigh-Ritz-Galerkian is what almost every single finite element code uses. ANSYS, Abacus, they all use this. Rayleigh-Ritz-Galerkian method. So we're going to take that 1D elasticity problem that we solved in closed form using Taylor series and variational principle, and now we're going to try to solve it from a numerical. And when you solve it numerically and you discretize it because of the numerical solution, you have to say it's an approximation. It's not an exact solution anymore. But we'll use some of the same things like variational principles and things like that as part of the solution. Okay. All right, folks, we ran over. I apologize. Have a good night. Have a good weekend.
Thank you, Professor.
Yep.